So there are relationships between the different properties of a gas. Those four properties are the pressure of the gas, the volume of the gas, the temperature of the gas, and we measure the amount of gas in moles. The properties are interrelated. If you change one or more of the others are going to change. It's going to affect the others. So there are different groups of gas laws. The simple gas laws are mathematical relationships describing the relationship between two properties. So we could look at the relationship between pressure and volume. To study that relationship, you have to keep the other properties the same. You have to keep the temperature and the amount of gas the same. And these laws were deduced from observations, holding two of the four properties constant and looking at variations in the other two. And these laws were observed a long time ago. The first law we'll talk about is Boyle's law. Robert Boyle lived back in the 1600s. It was a while ago. And he looked at the relationship between volume and pressure in a gas. So he did something like this. So he's got a tube here with some mercury in it, and there's a gas on this side, and this end is closed. And so he could measure the difference in pressure of the gas inside compared to outside. And he can also measure the volume of the gas. This is a nice cylinder, and so you can actually know, if you know the diameter, you can measure how tall the gas is, you can calculate its volume. And then what he would do is he'd do things like, well, let's add some mercury to the tube. We add more mercury, this side gets higher, but this side also gets higher. And what we're interested in is the difference in the heights. When he adds more mercury here, the mercury pushes down and squeezes the gas, and we see that the gas gets smaller. So the volume went down. The difference in the heights here is larger, so the pressure is greater. So you can squeeze a gas into a smaller volume by putting pressure on it. So he observed an inverse relationship between volume and pressure. If the pressure increases, the volume decreases. If the pressure decreases, the volume increases. They're inversely related. One goes up when the other goes down. We use graphs a lot in science because it helps us take numbers and make them more visual, and then we can see relationships much easier. So if you graph the volume of the gas versus its pressure, you get a curve like this. That's all very nice. As the pressure increases, the volume decreases. But curves like that are a bit hard to model, and so we like to look for a relationship where we can get a straight line. So Boyle's law is that the volume is proportional to 1 over the pressure. That graph of volume versus pressure is curved, but if we graph volume versus the reciprocal of the pressure, we get a straight line. So I'm going to show you that, and I'll come back to this slide. So this is some data I made up and graphed, and so here's that curve. That's volume versus pressure. If I take the inverse of the pressure, 1 divided by the pressure, and graph it with the volume, now I get a straight line. The straight line can be modeled using linear regression. We can figure out the equation for the line very simply, and then we can predict, well, if the pressure was out here, what would the volume be? And there's this nice relationship.
So, let's see, for example, if the volume is really high, will it ever reach 0?
That's an excellent question. We'll talk a lot more about that at the end of this chapter. But so if we were to continue increasing the pressure, well, actually it might be easier to look at this one. So as we increase the pressure, the volume gets smaller and smaller. And so if you extend that to, you would predict that at some point the pressure would be I mean, the volume would be 0. But is that actually possible? It's not, because the gas is made up of particles, and although the volume of those particles is very, very small, it is a finite volume.
So it's basically vertical and horizontal asymptotes.
Yeah, you can't actually get to 0. So that relationship, what we see is that as P increases, V decreases by the same factor. We could say that the pressure times the volume is equal to a constant. The equation for that line, the intercept would be 0, although you can't actually get there. So if the pressure and volume product at one point is a constant, the pressure times the volume at another point is also a constant. They're equal to each other. And so the way we typically represent Boyle's law is P1V1 equals P2V2. The pressure times the volume in the one circumstance is equal to the pressure times the volume in a second circumstance. And this is assuming constant temperature and constant amount of gas. So that's Boyle's law. Now, I'm going to talk about Boyle. I'm going to use his name. I don't require that you remember that Boyle studied pressure and volume. I have a hard time remembering who studied which law, but I think it's good to be familiar at least with these people's names. So, if we look at the particles and think about what are the particles doing, we can interpret Boyle's law. So here we have a piston assembly where this lid here can move up and down. So here we've got a 1 kilogram weight sitting on the lid. We've got some gas particles in here, and here we have a pressure gauge to tell us what the pressure is. So here the pressure is 1 atmosphere, the volume is 1 liter. If I cut the volume in half, then the pressure is going to double. Why does that happen? Well, we can think about what are these particles doing. We've got little trails here because they're moving. Gas particles are moving in straight lines until they hit something and then they bounce off. So here we have the particles are colliding with the walls of the container. If we make the container smaller with the same number of particles, the particles are going to collide more frequently with the walls of the container, right? I think of gas particles as being a little bit like kindergartners. So if you imagine, here are the kindergartners in a room, and the teacher stepped out, and what do kindergartners do? They kind of go wild, right? And so they're running around, and they're literally bouncing off the walls. If we take the same number of children and we cut the room size in half, they're going to run into things more frequently. Does that make sense? I know, it's kind of a weird. It's easier to picture than gas particles, though. Children bouncing off walls. So Boyle's law has implications for scuba diving. As you go down underwater, pressure increases. And the pressure increases very quickly because it's not air that's putting pressure on you, it's water, and water is much more dense. So for every 10 meters, every 10 meters that you go down, you experience about an additional atmosphere of pressure. So at the surface, you have 1 atmosphere of pressure from the air. You go down 10 meters, now you've got the original 1 atmosphere plus 1 atmosphere from the 10 meters of water. You go down another 10 meters, you've got 20 meters, that's 2 extra atmospheres of pressure, so a total of 3 atmospheres of pressure. That's 3 times the pressure that's at the surface. And you can imagine that that could affect your ability to breathe, right? Besides the fact that you're underwater. So I remember seeing these cartoons, right? And they'd have somebody hiding in a swamp or something, and they've got a straw up to the surface, and they're hiding under the water, and they're breathing through the straw. You could do that right below the surface. Like you can do that with a scuba, like a snorkeling mask, right? And you can snorkel. But if you were to go down 20 meters, even with a really big, wide snorkel tube, you wouldn't be able to breathe because the pressure of the water on your lungs would not allow your body to expand. So divers breathe pressurized air. So if the diver's down 20 meters and is breathing air that's pressurized at 3 atmospheres, takes a breath and holds it as he rises to the surface, now the pressure outside is 1 atmosphere, and you've got a pressure of 3 atmospheres inside your lungs. Does that sound like a good plan? No. The air in your lungs is going to want to triple in size. Your lungs don't expand that much. That could cause a lot of internal organ damage. So always exhale when rising. There's very good reason why you have to take classes and get certified and stuff before they let you scuba dive. Because it's actually really complicated. Snorkeling, not so much. You got to kind of coordinate your breathing so that you don't take an inhale when your snorkel's underwater, but other than that, you're pretty much okay. The scuba diving is much more complicated.
So since this is it's approximately that many atmospheric pressure, it wouldn't be considered exact also as a
no, it's not exact, but it's a nice relationship that's relatively easy to remember. It's approximate.
Would we use the number of sig figs?
Any question that involves the water and depth will be approximate, very approximate. So here's an example of a problem we might see, and this one has a lot of words. A snorkeler takes a syringe filled with 16 milliliters of air from the surface where the pressure is 1 atmosphere to an unknown depth. The volume of the air in the syringe at this depth is 7.5 milliliters. What's the pressure at this depth? If the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? So there's 2 questions here, and this is one, I'm not sure why they give this one as the first gas law problem. It's like, really, couldn't you start out with just a real straightforward one? But no, let's just hit them in the face with this complicated one. So this is one you might read and you're like, what the heck am I supposed to do with this? I would recommend drawing pictures just to kind of visualize what's going on here. So there's the surface of the water, okay, and we've got a syringe, right? So here's a syringe at the surface. It's closed off, and we've got a volume of air in there. And it says the volume of air is 16 milliliters. And then the snorkeler takes that syringe lower. So now the syringe is down here. And now it says the volume is 7.5. So I'm going to draw this with a smaller volume. This volume is 7.5 milliliters. Why did the volume of the air get smaller? Pressure. So the water is putting pressure on everything around it. If you've ever, dived down to the bottom of a deep swimming pool, you feel the pressure in your ears, right? You get all the way down the bottom, and you're like kind of uncomfortable. So as you go down, the water is putting pressure on the syringe. The gas can compress, and so as pressure is being pushed on the plunger, the gas will get smaller due to the outside pressure. So the first question is, what's the pressure at this depth? Well, they told us that the pressure up here was 1 atmosphere. You could have a problem like this where they don't tell you that the pressure at the surface is 1 atmosphere. You should be able to figure that out. If this is the ocean, at the surface of the ocean, that is sea level, right? Pressure at sea level is 1 atmosphere. So we've got that pressure up there, and then we're wanting to know why Mrs. K wrote V for pressure. That's what we're wanting to know. It's P. This is V. Sorry, it's Monday. It's going to be Monday all day long. We want to know what the pressure is down here, right? So we have Boyle's law, which relates pressure and volume. Pressure 1 times volume 1 is equal to pressure 2 times volume 2. So we just have to identify which is 1 and which is 2. And like with the dilution problems, it doesn't matter if I call this pair 1 or 2, as long as I put them together, because these two go together and these two go together. So since the surface was first, I'm going to call this 1. So this is pressure 1 and volume 1. We went down, and we have a new pressure and a new volume. So I'm going to take my equation, P1 V1 equals P2 V2, and I'm trying to find P2. So I need to rearrange this equation and solve for P2. So I need to get P2 all by itself. So if I divide this side by V2, that cancels out. And I do the same thing on the other side. And this is why we require algebra for this class, because there is some algebra. And if you're rusty and you don't remember how to do this, please ask me, and I can explain it to you and it'll come back. So now I'm going to plug in my pressures and volumes with their units. Pressure 1 was 1 atmosphere. Volume 1 was 16 milliliters. And volume 2 was 7.5 milliliters. And then let's look at what happens with the units. The milliliters are canceling out, and I'm left with the unit of atmosphere, which is good because I'm trying to find a pressure. So I take 1 times 16 and I divide by 7.5. This is going to tell me 2.133 repeating atmospheres. Now these are not precise measurements. We've got 2 significant figures on everything, so this should have 2 significant figures. And I can say the pressure at that depth is 2.1 atmospheres. That's the answer to the first question. What's the pressure at this depth? Any questions about that? The next question, if the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? This adds an aspect of problem solving. So that is a relationship, 1 atmosphere per 10 meters. So I could say 1 atmosphere for 10 meters of depth. That's a relationship. I have to be a little bit careful though, because at the surface I already had 1 atmosphere. So going down, I've had an increase of how much? Down here, it's 2.1. What's the difference between those? 1.1. I've had an increase in pressure of 1.1 atmospheres. I get 1 atmosphere of increase for every 10 meters. Where should I put this? So it'd be best to use the unrounded version here. So if I subtract the initial pressure, then I get 1.133 atmospheres. Oops. So 1.133 additional atmospheres is going to be 10 meters for every 1 atmosphere. So 11 meters. That's a question that you can only solve by understanding what's happening and thinking about it. Life is complicated, and we can't learn rote memory how to solve this kind of problem and that kind of problem and be able to cover everything. It's just not possible. So we do have to think. Any questions? .1 atmospheres, 11 meters. Okay, J.A.C. Charles studied the relationship between volume and temperature. This is in the 1800s. He found that the volume of a gas was directly proportional to its temperature. Not inversely proportional, but directly proportional. So here, volume is proportional to temperature. We typically express Charles' law as this. V1 over T1 is equal to V2 over T2. And again, I'm not going to make you remember that that's Charles' law. This bottom point here is very, very important. The temperature must always be expressed in kelvins. The volume of a gas is directly proportional to its absolute temperature. If we do this in Celsius or in Fahrenheit, we could have a place where the temperature is 0. And then what would happen to our equation? We'd have some volume divided by 0, and it would be undefined. We can't have a temperature unit that has 0 in it. We also can't have any negatives, because then we could get a negative volume, which is also impossible. So the Kelvin scale is used for gases because there are no zeros or negative numbers. So here we have a Charles' law graph. We have volume versus temperature. And we see that as you increase the volume, the temperature increases. And these are for different amounts of gas. This is 1 mole and half a mole and 1/4 of a mole of gas. Here we have listed the Celsius temperatures, 0, 100, etc. If I take these 3 lines and extrapolate them, meaning I'm going to draw the line past where I actually have data, what I find is that all of those lines intersect at the same point. At 0 volume, they intersect at minus 273.15 degrees Celsius. So that temperature is called absolute 0. That's the theoretical lowest possible temperature, because negative volume is not possible. So let's look at what the particles are doing to help us understand this. Here we have 2 balloons. We put actually it's the same balloon. We put the balloon in ice water and the balloon shrinks. So lower temperature, the volume is smaller. We put the balloon in boiling water, temperature is higher, the volume goes higher. This is something you can try at home. Don't start out with a really, really full balloon and stick it in boiling water, because it'll pop. Start with kind of a medium, give it room to expand. What's happening here is that the particles move faster at higher temperatures. Temperature is a measure of the average kinetic energy. I think I've talked about this before. So you guys are in the solid state of students right now. You're sitting, and I'd say you're at a pretty low temperature. Everybody's pretty calm. But if we were all just antsy and just wanting to get out of here and wiggling and bouncing our legs, that would be the equivalent of a higher temperature. You haven't melted, you're not moving around yet, but it's a higher temperature. It's more movement, more kinetic energy. Here in the gas state, things are not fixed. They're actually moving. And so now the gas particles at a higher temperature are moving faster. What that means is they're going to hit the containers more frequently, the walls more frequently, and they're going to hit harder, right? So the gas particles have more energy. So this is like someone very unwisely giving Red Bull to the kindergartners, right? They're going to run around faster now, right? They're going to run into each other and to the walls of the classroom more often. They're going to run into each other harder. Somebody's going to get hurt, right? Hopefully no one will put out an eye, but they're going to run into each other a lot. So the balloon can expand and contract. So it will keep the pressure constant, relatively. So the increased hitting the pressure will cause the balloon to expand and cause us to have the same pressure. So we're going to have the same pressure here and the same pressure here, and that's possible because the volume can expand. That makes sense? That's kind of what I said. You get more collisions, and the collisions are more energetic, so the only way for the pressure to stay the same is for the gas to occupy a larger volume. So the kindergarten students, if they're all charged up on caffeine, now we have to put them in a bigger classroom to go back to the normal amount of people running into each other. There's a balloon in liquid nitrogen, and as that gas condenses, it will eventually liquefy and become much, much smaller. Won't go to zero though, because it is matter. It has some volume. And this is a picture of a hot air balloon. I remember seeing these as a kid and being kind of mystified, because I knew from experience with balloons that if you blew up a balloon with air, unlike in the cartoons, it won't float, right? Still fun to play with, but it's going to fall on the ground. The only way you get them to float is if they've got helium in them, right? And if you put a hole in your balloon, all the helium comes out and it goes flat. So this is my child mind looking at this and thinking, how does that work? This is a balloon with a really, really big hole in it, and it's only full of air. And yet, not only is it floating, it can carry people into the air, right? How crazy is that? Charles' law in action. There's this giant burner here, and what it does is it heats the air inside the balloon. The air expands because it can, right? There's this big hole here. So the pressure inside the balloon is equal to the pressure outside the balloon. But the gas expands and a lot of the air comes out the bottom. Now we have the particles, but there's more space, the density goes down. And so like an air bubble in water floats to the surface, this air with lower density compared to the air around it also floats to the surface. And you can control the density of the air with the big burner here. You want to go up, you put more fire, you make it hotter. You want to come down, you reduce the flame. You don't want to do that too quickly because you'd like to come down in a controlled manner, right? Thing is, you really don't have much control over direction in a hot air balloon. The air moves sometimes in different directions and different speeds at different altitudes, so you can control it a little bit that way by going further up or down, but you can't say, no, I want to go left here. There's no steering. Yes?
My aunt used to take tours of those.
Mm-hmm.
And one time, when she was taking a tour, they were having like a bad, not windstorm, but just
A lot of turbulence?
Yeah,
Mm-hmm.
turbulence, and they were coming down pretty fast. She told everyone to get down, but one person didn't, and she fell out and died.
Oh, gosh.
Yeah,
That's a...
What's it doing anymore?
Yeah. So there was a lot, for my YouTube people, there was a balloon tour and there was a lot of turbulence, and so they're coming down fast, and the operator told everybody to get down in the basket, and of course there's always one person that doesn't listen, and that person fell out and died. That's sad. It looks really cool to go up in one of those, but I've never actually done it because it also looks like really, really scary. My fear about heights is that I'm going to suddenly lose my impulse control and I will hurl myself over the edge. I don't like to stand too close to railings. The Grand Canyon, I'm like, no, I'll look at it from back here, thanks. Because I don't know, it's just this irrational fear. I've never done that, but, you know, part of your brain says, what would happen if I just drove off this cliff? Impulse control is what says, no, don't do that. And I've shared some of my disturbing personal thoughts. Okay, Charles' Law problem. This is a more regular kind of problem. We're going to hear a lot about pistons and containers with movable lids because we have to be able to have the volume change. A gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 degrees Celsius to 155 degrees Celsius, what's its final volume in milliliters? Yes?
So for when you do concentration, you know it's always moles or liters. For any of these, is there like a specific
Unit?
Yeah. It's just
That's an excellent question. So molarity is always moles per liter. The one thing we have to be really careful about with the gas laws is temperature. Temperature has to be in kelvins. The other ones, it really depends on the problem. For these simple gas laws, like here we've got milliliters for volume, perfectly fine. We could do it in gallons or liters, it would also be fine. But the temperature here is given to us in Celsius, and that's not fine. We need kelvins. That's an excellent question. I think it's useful to take this information and just make a table out of it because it can be kind of confusing to look at it interspersed with all those words. So I like to make a table. And so there's going to be a header row and then 2 rows with numbers. And so we'll call this 1 and this 2 just because. And so I can set that up and then I go through the problem and I can just write the numbers down as I come to them. So the first number I come to is 88.2 milliliters. Okay, well, I'm going to put this up here, 88.2 milliliters. So that's going to be a column. And then I ask myself, well, what is that? Is that volume or temperature or pressure? It's volume, right? Initial volume. It actually says volume. So I'm going to label this V for volume. If it didn't say volume, the unit milliliter should tell me it's volume, because it's the unit volume. So that's the initial volume, and it says we heat the gas from 35 to 155. So this is the initial volume. The initial temperature is 35 degrees Celsius, and the final temperature is 155 degrees Celsius. This is temperature. But before we go any further, we need to remember this should be in Kelvin. So we're going to convert it right now before we forget. So the relationship Kelvin equals degrees Celsius plus 273.15. The book is sloppy about this, which bothers me a little bit, but we'll have to deal with it. Sometimes it's very important to have the 0.15, other times it doesn't matter. I think it's best to always use the 1.5, but in a situation like this, my temperature is to the nearest 1 degree, and so if I use 273, it's going to be fine. If my temperature went to the tenths or hundredths or something, then I should use all the digits. So I've got 35.273. So this is 308 Kelvin. And I'm going to convert the other one also. 155 plus 273. 428 Kelvin. And it says, what's its final volume? And I should have one square, it's actually a rectangle. I should have one cell empty. So that's volume 2. I'm going to call this volume 2 because it's the volume column in the second row. This is a Charles Law problem, but what happens on an exam is you just get a problem without a label. And so what we need for this is an equation that has volume and temperature and 1s and 2s in it. And so that's going to be V1 over T1 is equal to V2 over T2. And I'm going to show you later how you can very quickly derive these relationships so that you don't actually have to memorize them. So this is the sort of equation that gives people problems because there's fractions. So I would highly encourage you to clear the fractions first by cross-multiplying to avoid some of the issues that happen, say, with the density where you screw it up. So cross-multiplying, to refresh your memory, is you take the numerator on one side and multiply it by the denominator on the other side. So that's V1 times T2. And that's going to be equal to the denominator of the first side times the numerator of the second side. Multiplication, the order doesn't matter, so if you have T2 V1 or V1 T2, it's the same. Got rid of the fractions, now it's easier to rearrange. I'm trying to solve for V2. So I want V2 by itself, so I'm going to divide by T1 to get V2 all by itself, and I have to do the same thing to both sides. V2 is equal to V1 T2 over T1. It's very easy to transpose numbers here, get your 1s and 2s mixed up. So be very, very careful when you do that. You really, really need to show your work for this. The minimum for showing your work is to write out the rearranged equation and then write it with the numbers plugged in and then the answer. If you're a little iffy on your algebra, you should also write out how you rearranged it so you can go back and check. So I'm going to pick these numbers out of my table, being careful to pick the correct numbers. V1 is 88.2 milliliters. You always want to include the units. T2 is 428 Kelvin. And in the denominator, I have T1, which is 308 Kelvin. The Kelvin units cancel out. So I have 88.2 times 428 divided by 308. All of those have 3 sig figs. So that's going to give me 123 milliliters. For the simple gas laws, we can ask ourselves, well, does it make sense? I took this gas and I heated it. Do I expect it to get bigger or smaller? Bigger. So my second volume should be larger than the first. 123 is larger than 88, so that's encouraging. Doesn't prove anything, but it's encouraging. So let me show you why we can't just use Celsius, even though the units would cancel out. 88.2 milliliters. And if I have 35 degrees Celsius plus 273 divided by 155 degrees Celsius plus 273. Can I cancel out the plus 273? I can't. Converting milliliters to liters, things like that, all the conversions are just multiplying and dividing. Temperature conversions always involve something adding or subtracting. And so the conversion doesn't cancel out. And so we can't do that. We get a different answer If we use Celsius, we get 19.9. So if I mistakenly canceled those out, I get 19.9 milliliters. That's a wee bit different, right? So that's just wrong. You can't do that. You have to use Kelvin. And I will try to trick you with that. And you'll see, you're like, well, if we have to use Kelvin, why do they always give us the temperature in Celsius? Because we always measure temperature in Celsius. I've never seen a thermometer that has kelvins on it. If you need kelvins, you just add 273.15. There's no need for another thermometer. So we're going to do a lot of that, converting Celsius to Kelvin. It's possible that you might get it in Fahrenheit. I consider that a little mean, but it could happen. Any other questions? 123. Okay, conceptual connection. So the pressure exerted on a sample of a fixed amount of gas is doubled at constant pressure. And then the temperature is, in kelvins, is doubled at constant pressure. What's the final volume of the gas? Now, you can be really good at solving problems like the previous one and have a heck of a lot of trouble with something like this. But this really tells us, do we actually understand, or are we trained monkeys doing problems? So if I've got this sample of gas and I double the pressure, what's that going to do to the volume? If I double the pressure, it's going to double the volume? It's going to cut it in half, right? So I can think about this. So 2 times pressure would give me 1/2 the volume, right? And then it says the temperature in kelvins is doubled. So if I go 2 times the temperature, what does that do? Multiplies by 2. So then I've got 2 times 1/2 the volume. I'm back to my original volume. So all these answers, and the correct answer is E. The final volume is the same as the initial volume. Doubling the pressure made the volume cut in half, but doubling the temperature doubled the volume back up to its original amount. So you need to be able to answer questions like that too. Any questions? Avogadro's law, we've heard his name before. Amadeo Avogadro, of Avogadro's number. He was the first one to formally state the relationship between the volume of a gas and the amount of gas. The volume of a gas is proportional to the number of particles, molecules or atoms of the gas. And so that's why the amount of gas is measured in moles, because moles is a counting number. So, not Amadeo, Avogadro. Avogadro's law says that volume is proportional to amount of gas in moles, assuming constant temperature and pressure. And so that can be described this way, V1 over N1 equals V2 over N2. We're counting gas molecules using moles. So what's interesting about this is under the same conditions, equal volumes of gases have equal numbers of molecules. Doesn't matter what the gas is, because the volume of a gas depends on the number of particles, not how big they are, not how much they weigh. If we graph volume versus number of moles, we see that at 0 moles, the volume would be 0, because there's nothing in there, right? And as we double, well, you can't double 0, but as we increase the volume, as we increase the moles, the volume increases proportionally. So which action causes the volume of a gas sample to increase? Decreasing the pressure, decreasing the temperature, decreasing the number of moles, or none of the above? Well, let's go through them one at a time. If I decrease the pressure, what does that do to the volume? It allows the volume to get bigger, right? So that causes the gas to increase in volume. So that's, whoops. If I decrease the temperature and make it colder, does the gas get bigger or smaller? It gets smaller. If I decrease the moles of gas, if I take gas out of the balloon, does it get bigger or smaller? It gets smaller. Yeah, that's ridiculous. A lot of this you can answer by thinking about what would happen if this was a balloon, right? So if I decrease the pressure, if I maybe take it way up high in the atmosphere, I decrease the pressure, the balloon's going to get bigger, right? So it's A. Avogadro's law. Problem. Chemical reaction occurring in a cylinder equipped with a movable piston, there's that again, produces 0.621 moles of a gaseous product if the cylinder contained 0.10 moles of gas before the reaction and had an initial volume of 2.18 liters. What was its volume after the reaction? Assume constant pressure and temperatures and that the initial amount of gas completely reacts. Okay, so all those words, we need to pull the numbers out. Let's make a table. Now 1 and 2. First number I come to is 0.621 moles. So I need to label this column. I have 4 variables. Pressure is P, volume is V, temperature is T, and moles of gas is N. You may want it to be M, but it's not, it's N. Number of moles. How's that? So that's the product. If the gas cylinder contained 0.10 moles of gas before the reaction, so that's also moles. That's a 6. Let's just try that again. It's a 6. So 0.120 moles. And had an initial volume of 2.18 liters. So this 2.18 liters, this is the initial volume, this is the moles of gas before the reaction. These two numbers go with each other. So 0.12 moles and 2.18 liters. So these two are related. Now I ended up calling those 2, even though that's the first condition. Doesn't matter. I just need to pair them up correctly. So that is a volume, so I'm going to call this column V. And then I have one blank. That's going to be V1. So they're asking the volume after the reaction. So this is the moles after the reaction, and so I'm going to try to find the volume. If it bothers you that the 1s and 2s are backwards, you can change that. It doesn't matter. So I need a relationship with N and V. It's V1 over N1 equals V2 over N2. Again, we've got fractions here. Good idea to cross multiply. V1 N2 equals N1 V2. I am trying to find this missing piece, V1. So I'm going to divide both sides by N2 so I can get V1 by itself. So N1 is 0.621 moles, and V2 is 2.18 liters, and N2 is 0.120 moles. And I look at the units and the moles cancel out. And then I do the math. .67689 is what my calculator says. Everybody's got 3 sig figs. 0.677 liters. Did I do that okay?
Would 0.120 moles and 2.18 be considered N1 and V1 because it says initial and before reaction?
So the 1 and 2, you can use that to indicate the first and the second condition, but you don't have to. So yes, this happened before, but because of how I went through the problem, I came across this one first. So if you want to change the labels here, that's fine. But 1 and 2 just means that N1 and V1 are together and N2 and V2 are together.
It should be 0.120 moles times 2.1 divided by 0.621.
I think you just put the calculator on. I'm getting 11.2815.
I divided by 2. How did that happen? So 0.621 times 2.18 divided by 0.12. Yeah. Yep, screwed up again. So 11.2815, does that look better? Yeah. 11.3. I was going to mention this, and I didn't intend to demonstrate it so dramatically. When you do the calculation, do it twice. You punch it through your calculator, write the answer down, press clear, punch it in again. You get the same number? Awesome, you're probably right. Get 2 different numbers? Go for best 2 out of 3. You would be amazed at how many worksheets and lab reports I'm getting where they've got everything set up right, and then the number's wrong. And I write bad math, and I take a point off. You have a calculator. Get the math right. Like, oh, but I got it. Yeah, but the answer's still wrong. And so out in the real world, your intentions don't matter. What matters is, did you get the right answer? They lost the Mars orbiter because they had the wrong unit. Oh, but we did all the calculations right except for that. Doesn't matter, the thing still crashed. Can't take it back, right? So thank you for calling me on that. 11.3. Anything else? We can look at this, and this would have at least made me wonder a little bit. We can anticipate, should this get bigger or smaller? So we started with 0.12 moles. I lost my pointer. 0.12 moles, and then we end up with 0.621 moles. We would expect the volume to get bigger, and significantly bigger, not just a tiny bit like my first bad answer. And so here we went from 2 liters to 11 liters, and so that's encouraging. And then there's the answer. That's correct. Here's another example. This is another weird one. Scale model of a blimp rises when it's filled with helium to a volume of 55 cubic decimeters. When 1.1 moles of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant temperature and pressure. Doesn't that seem a little funny? You want this blimp to go up, and you do that by adding more helium. I'm adding mass to it, and that's going to cause it to go up. Okay. So this is another one where you might want to draw a picture, and it can be a really ugly picture. So here's my blimp. Oops. Yeah, my program's not working. Actually, it's my pencil's dead. That's a blimp. I know it kind of looks like a fish. And here's it's kind of a squishy, not filled up blimp. So the blimp will rise when it has a volume of 55 cubic decimeters. Cubic decimeters, I don't like that unit. It's okay, it'll cancel out. When 1.1 mole of helium is added to the blimp, so the blimp was empty to start with, and so we put in 1.10 moles of helium, and that gave us a volume of 26.2 cubic decimeters. I don't write very well with my finger. So we've got N, and we've got 2 volumes, right? So we could make a table with this. So here we have our SAD half-filled blimp, and that has 1.10 moles in it. So that's N. And the volume is 26.2 cubic decimeters. And up here, we want the volume to be 55.0 cubic decimeters. So we can solve for N2. N2 is the amount of gas in moles when it's floating. That's not the direct answer to the question, how many more grams do we have to add? But it's a step in the right direction. V1 over N1 equals V2 over N2. We're solving for N2. So you can do it the way I've been showing you with cross-multiplying. If you get it, you can rearrange this equation by just moving things diagonally across the equal sign. So here I have N2 in the denominator. I can move it upstairs on the other side, and I can take V1 and put it downstairs. And this N1 I can move from downstairs here to upstairs there, and I can actually just rearrange this by looking at it. And if you're like, wait a minute, how did you do that? Either ask me to show you during lab or do it the other way. Then I plug my numbers in. And 1.10 moles. Volume 2. And volume 1. The cubic decimeters uncomfortable unit cancels out and goes away. Bye-bye. 1 times 55, 1.1 times 55, divided by 26. So N2 equals 2.3269 moles. It's not the answer yet. This is the amount of gas in moles when it's floating. So up here we've got 2.33 moles. This is an adding gas problem, and I will try to trick you with one of these. Okay. So the question is asking, how much gas do we have to add? How much more do we have to put in to make it float? So we can find the amount of gas in moles. It's the final amount. Oh my goodness. 2.3269 moles minus the starting amount. That's how many moles need to be added. And the question says, how many grams? Well, it's helium. Molar mass from the periodic table, multiplied by 4.003 grams per mole for helium. .9113 4.91 grams. So I have to add 4.91 grams. Any questions? Just how to take a straightforward, simple gas law problem and make it complicated. Complicated's more interesting. I didn't have the number on that one. I didn't put the answer on that one. Okay.